Imagine, if you will, that we're just drifting out here in the vast, quiet expanse of space. The stars twinkle around us, like tiny, distant diamonds scattered on black velvet. They seem so peaceful, don't they? So steady, so eternal. But the truth is, some of these seemingly serene points of light are living incredibly dramatic lives, and some are destined for the most spectacular, breathtaking, and utterly cataclysmic end imaginable. We're talking about supernovae. Now, a supernova isn't just a big explosion. Oh no, it's far more than that. It's the ultimate cosmic grand finale, the most powerful explosion in the entire universe. Think of the biggest firework display you've ever seen, multiplied by 1 billion, and then multiplied by another billion, and then some. It's a moment of furious, unfathomable power, where a single star, in its dying gasp, can briefly outshine an entire galaxy, a whole island of hundreds of billions of stars. Can you even begin to picture that? One lonely star, suddenly brighter than everything else in a cosmic city. If you like listening to quiet stories about space and stars, please tap the like button. It helps others find this peaceful place too. And if you want to come back for more calm journeys through the universe, please like and subscribe. Enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. So, what kind of star ends its life in such a dramatic fashion? Well, there are a couple of ways a supernova can happen, but the most common and truly spectacular type involves a truly enormous star. Imagine a star that is absolutely colossal, a gigantic sun perhaps 8 to 15 times, or even more, the mass of our own gentle sun. These are the heavyweights of the cosmos, the stellar giants that live life in the absolute fastest lane. These massive stars don't live for billions of years like our sun. Oh no, they burn through their fuel at an incredibly furious pace, like a roaring bonfire instead of a cozy campfire. Their lives might last only a few million years, and during this short, intense life, they shine with a brilliant, fierce blue or white light, pouring out immense amounts of energy into space. You can almost feel the sheer, overwhelming power radiating from them, even from light years away. They are the dazzling, yet fleeting, spotlights of the universe. And deep inside these giants, something truly incredible is happening. While our sun spends its life patiently fusing hydrogen into helium, these massive stars are like cosmic chefs, cooking up heavier and heavier elements. They fuse hydrogen into helium, then helium into carbon and oxygen. But they don't stop there. Their immense gravity keeps squeezing their cores, making them hotter and hotter, denser and denser. This allows them to start fusing carbon into neon and magnesium, then neon into oxygen and silicon. It's like building an onion, layer by layer, but with different nuclear reactions happening in each layer around the star's core. This process continues, building up heavier elements closer and closer to the very center of the star. It's a furious, desperate race against time, as the star uses up its fuel more and more quickly to support its own colossal weight. And then, at the very heart of it all, the star forms its final fateful layer, iron. And that, my friend, is where the story of calm fusion comes to a sudden, screeching halt, setting the stage for the most spectacular show in the universe. Iron is the ultimate cosmic dead end. This explosion isn't just about a star dying, it's about the universe being reborn, enriched with all the ingredients necessary for new worlds, and even life itself, to eventually emerge. It's a truly humbling thought that the very gold in a ring, or the tiny bit of uranium in an old clock, was created in such a majestic, violent, distant event. After the initial, blinding flash subsides, what remains is an expanding, incredibly hot bubble of gas and dust. This is the supernova remnant, the ghostly afterglow of a star's colossal demise. Imagine yourself floating near it now. The light has softened from that blinding intensity, but you can still see the vast, turbulent cloud expanding outwards, ever so slowly. It glows with ethereal colors, vast tendrils of gas illuminated by the leftover energy from the explosion. You might see shimmering greens where excited oxygen atoms are radiating light, or deep, fiery reds from hydrogen. These cosmic clouds can stretch for hundreds of light years across, slowly dispersing over thousands of years, a beautiful, sprawling memorial to the star that once was. As this supernova remnant expands, it sweeps up the sparser gas and dust already floating in the interstellar space around it. It's like a colossal cosmic broom, gathering up material and, in doing so, creating denser pockets. These shockwaves from the supernova can even act as cosmic triggers, pushing existing clouds of gas and dust together, making them collapse under their own gravity. This is how the death of one star can directly lead to the birth of many new stars and star systems. It's a powerful reminder that in the universe, destruction and creation are often two sides of the same coin, constantly linked in a grand, unending cycle. Now, while the collapse of a massive star's iron core is one spectacular way a supernova can occur, it's not the only way. There's another, equally fascinating type of supernova, and this one involves stars that are much smaller, stars that should, by all accounts, fade away quietly into white dwarfs. This type is called a Type Ia supernova, and it's truly a testament to the complex, intricate relationships that stars can have with each other. Imagine a stellar odd couple, two stars caught in a gravitational dance. One is a white dwarf, that incredibly dense, Earth-sized remnant of a sun-like star that has finished its life. The other is a companion star, perhaps a red giant that has swollen up, or even a main sequence star that's just a bit smaller. These two stars are locked in orbit around each other, gracefully circling their shared center of gravity. Sometimes, if they are close enough, the white dwarf's incredibly powerful gravity can begin to pull material directly off its companion star. Imagine a cosmic vacuum cleaner, steadily siphoning gas from its partner. This gas, mostly hydrogen and helium from the companion star's outer layers, forms a swirling disk around the white dwarf, slowly spiraling inwards and piling up on the white dwarf's surface. It's a very gradual process, happening over thousands, even millions of years. As this fresh hydrogen and helium accumulates on the white dwarf, it gets incredibly hot and dense, compressed by the white dwarf's immense gravity. The pressure and temperature at the base of this accumulated layer build and build, until suddenly, the hydrogen on the surface of the white dwarf ignites in a runaway nuclear reaction. This isn't the whole white dwarf exploding, but a powerful, rapid fusion event on its surface. This brief, brilliant flash is what we call a nova. It makes the white dwarf temporarily brighten by thousands of times, before it settles down again, ready to potentially accrete more material and flare up again in the future. It's like a recurring stellar hiccup, a temporary brightening. But sometimes, the white dwarf is particularly greedy, or its companion star is particularly generous, and the white dwarf gains so much material that it reaches a critical mass. There's a specific limit to how much mass a white dwarf can hold before its internal electron pressure can no longer support it. When it reaches this limit, it's like a cosmic tipping point. The entire white dwarf, no longer able to resist its own immense gravity, begins to collapse further. This collapse rapidly heats the entire white dwarf, triggering a runaway fusion reaction of the carbon and oxygen within its core. And when that happens, the entire white dwarf detonates, not just its surface but the whole thing. The star is completely obliterated in a colossal explosion. This is a Type Ia supernova. These are incredibly important for us here, far away in the cosmos, because they are remarkably consistent. They all explode with almost the exact same intrinsic brightness. Think of them as cosmic standard light bulbs, shining with the same wattage no matter how far away they are. This makes them invaluable tools for astronomers to measure vast, immense distances across the universe. Imagine trying to figure out how far away a city is just by how bright its lights appear, knowing that all the streetlights there are the exact same brightness. That's how we use Type Ia supernovae. They are truly magnificent, cosmic signposts, marking colossal distances and revealing the grand scale of the universe. They are truly magnificent, cosmic signposts, marking colossal distances and revealing the grand scale of the universe. So, we've explored the two main paths to a supernova, the catastrophic collapse of a massive star and the runaway explosion of a white dwarf stealing too much from its companion. Both are utterly spectacular, but their importance goes far beyond mere cosmic fireworks. Supernovae are, quite simply, the universe's way of ensuring its own future and ours. Imagine all those heavy elements created in the stars, the carbon, the oxygen, the iron, the gold. They are trapped inside the star's fiery cores. Without a supernova, they would largely stay there, forever out of reach. But these explosions are the ultimate cosmic delivery service. They blast these life-giving ingredients out into the vast emptiness of interstellar space, scattering them far and wide. It's like a colossal seed spreader, ensuring that the next generation of stars and the planets that form around them will be rich with all the materials necessary for complexity. Picture the interstellar medium, that thin, diffuse gas and dust between stars. It's constantly being enriched by these events. Every time a supernova goes off, it adds more carbon for rocky planets, more oxygen for water and air, more iron for planetary cores, and, eventually, for the very blood that flows in living beings. We are, quite literally, made of stardust. Every atom heavier than hydrogen and helium in your body, in the ground beneath your feet, in the air you breathe, was forged in the heart of a star and scattered by a supernova. It's a profound, humbling connection to the vast, violent, and beautiful cosmos. Supernovae are relatively rare events in any given galaxy. In a galaxy the size of our Milky Way, a supernova might occur, on average, once or twice a century. That might sound infrequent, but considering how many hundreds of billions of stars there are, it makes sense. Imagine the sheer scale of the galaxy. Finding one star exploding among so many is like finding a single, incredibly bright flashbulb going off in a city of billions of lights. But across the entire observable universe, with its billions upon billions of galaxies, supernovae are happening all the time, somewhere, at any given moment. Every second, many supernovae might be flaring up across the vast cosmic tapestry, each one a distant beacon of stellar death and cosmic rebirth. Astronomers are always on the lookout for these cosmic explosions. They use powerful telescopes to scan the night sky, looking for sudden, unexpected brightenings of distant stars or entire galaxies. When a supernova is spotted, it becomes a race against time. Scientists then turn their most advanced instruments towards it, observing its light as it changes over days and weeks. By studying the light, they can figure out what elements were created in the explosion, how fast the material is expanding, and even the type of supernova it was. It's like being cosmic detectives, piecing together the story of a star's final moments from the fading echoes of its light. Beyond just the visible light, some supernovae also release an incredible burst of tiny, ghostly particles called neutrinos. These particles are so small and interact so weakly with matter that billions of them pass right through you every second, undetected. But when a supernova happens, a colossal shower of neutrinos is produced, and sensitive detectors here on Earth can pick them up. It's like feeling a faint, invisible tremor from across the universe, a subtle confirmation that one of these magnificent explosions has just occurred. It adds another layer to our ability to feel these distant, powerful events, even when they are light years away. And there's an even more exotic way we can sense the most violent supernovae, through gravitational waves. Imagine the fabric of space and time, not as a rigid, unchanging stage, but as a giant, flexible trampoline. When incredibly massive objects move or collide, they create ripples in this trampoline. A core collapse supernova, with its dramatic, rapid implosion and rebound, is like dropping a bowling ball onto that trampoline. It sends out tiny, fleeting ripples of pure gravity that travel outwards at the speed of light. These ripples are incredibly faint by the time they reach us, but highly sensitive detectors on Earth can pick up these minuscule stretches and squeezes in space itself. It's like listening for the echo of a giant bell ringing billions of light years away, a silent wave passing through everything. Detecting these gravitational waves gives us a brand new sense to understand the most violent moments in a star's death, providing insights that light alone cannot. Supernovae aren't just theoretical concepts or distant flashes. They have actually been seen by humans throughout history, long before we even understood what they were. Imagine looking up at the night sky and seeing a new star suddenly appear where there was nothing before, or seeing a familiar star suddenly become incredibly bright, shining even during the daytime for weeks or months. For ancient astronomers, these were profound, mysterious events. One of the most famous historical supernovae occurred in the year 1054. Ancient Chinese and Arab astronomers recorded seeing a guest star that was so bright it was visible in daylight for weeks. Today, We know that Guest Star was a supernova, and what's left of it is the beautiful Crab Nebula, a glowing supernova remnant that we can still observe through telescopes. It's a direct link to a cosmic event that happened nearly 1,000 years ago, still expanding and glowing. Another famous one happened in 1604, observed by Johannes Kepler and many others. This supernova was also visible to the naked eye, even in daylight, and puzzled astronomers who believed the heavens were unchanging. These historical observations, sometimes meticulously recorded by cultures around the world, provide invaluable data points, helping us understand how often supernovae occur and how their brightness changes over time. It's like finding old family photos that show a rare and incredible event, helping us piece together the past. And what about the future? Could we ever see a supernova ourselves? In our own Milky Way galaxy? It's certainly possible. There are stars in our galactic neighborhood that are massive enough and old enough to be considered candidates for a supernova in the relatively near cosmic future. One of the most famous candidates is Betelgeuse, a red supergiant star that makes up part of the constellation Orion. It's truly colossal, hundreds of times larger than our Sun, and nearing the end of its life. Astronomers believe it could go supernova anytime in the next 100 years, or even tomorrow. If Betelgeuse were to go supernova, it would be an absolutely breathtaking sight. It would appear as an incredibly bright point of light in our night sky, perhaps even visible during the daytime for a few weeks or months. It might even be as bright as the moon, or even brighter for a short period. Imagine stepping outside and seeing a second moon, or an incredibly brilliant star blazing in the sky. It would be a profound, once-in-a-lifetime cosmic event, a direct witness to the grand, violent, beautiful end of a star, right in our own galactic backyard. You might even feel a subtle increase in the neutrino count, though you wouldn't feel the particles themselves. But don't worry about being too close to a supernova. For life on a planet like ours, a supernova would need to occur dangerously close to be truly harmful, perhaps within a few tens of light years. The intense radiation from such a close blast could strip away a planet's atmosphere or cause other devastating effects. Thankfully, there are no known supernova candidates that close to us. The vastness of space provides an incredible buffer, allowing us to appreciate these magnificent cosmic spectacles from a safe, awestruck distance. Thankfully, there are no known supernova candidates that close to us. The vastness of space provides an incredible buffer, allowing us to appreciate these magnificent cosmic spectacles from a safe, awestruck distance. So, while the immediate, brilliant flash of a supernova might last only weeks or months, its legacy echoes through the cosmos for millions, even billions of years. Imagine, floating there, watching the immense, glowing supernova remnant continue to expand. It's like a colossal, slowly inflating bubble of superheated gas and dust, pushing against the thinner material in the interstellar medium. These expanding shockwaves are incredibly important. They stir up the gas and dust in our galaxy, preventing it from just settling into a uniform, boring soup. It's like a cosmic whisk, constantly mixing things up, creating turbulence, and helping to form denser regions where new stars might eventually coalesce. Beyond simply scattering elements, supernova remnants are also thought to be incredible accelerators of tiny, high-energy particles called cosmic rays. These are not really rays of light, but incredibly fast, moving atomic nuclei and electrons. Imagine microscopic bullets fired across the galaxy at nearly the speed of light. These cosmic rays can actually penetrate deep into interstellar clouds, affecting their chemistry, and even playing a small role in triggering star formation. So, the death of a massive star doesn't just spread new elements, it also energizes the galaxy, creating a vibrant, dynamic environment. And let's not forget the incredible objects left behind at the very heart of these explosions. We talked about neutron stars, those impossibly dense spheres, packed solid with neutrons. They are extreme worlds, governed by the most intense gravity and powerful magnetic fields imaginable. Some neutron stars are also pulsars, sending out regular beams of radio waves as they spin, like cosmic lighthouses. Imagine standing on one, if you could, where a single teaspoon of material weighs billions of tons. The gravity would be so strong, you wouldn't just be flattened, your very atoms would deform. And some neutron stars have magnetic fields, so incredibly strong, thousands of times more powerful than anything we can create on Earth, that they are called magnetars. These magnetars can unleash powerful bursts of X-rays and gamma rays, cosmic flares that briefly outshine our sun by a colossal margin. It's a powerful reminder of the exotic, extreme physics that result from a star's violent death. Then there are the most profound remnants of all, black holes. When the most massive stars collapse, the gravitational squeeze is so intense that even the incredible density of a neutron star isn't enough to stop it. The core keeps collapsing, getting smaller and smaller, until all its mass is concentrated into an infinitely tiny point. This creates a region of space where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. Imagine trying to shine a flashlight into a bottomless well, but the well is made of pure gravity, and the light just curves back in on itself. Black holes are not cosmic vacuum cleaners that indiscriminately suck everything up. Their gravity is just like any other object of the same mass, but only becomes inescapable if you get too close. However, if gas and dust, or even other stars, wander too near, they can be pulled into a swirling accretion disk around the black hole, heating up to incredible temperatures and emitting powerful X-rays as they spiral inward, eventually disappearing beyond the event horizon. This is often how we detect black holes, not by seeing them directly, but by observing the intense light from the material dancing its final, fiery waltz around them. So, from the initial, quiet gathering of gas and dust, through the long, luminous lives of stars, to their cataclysmic supernova deaths, and the formation of these extreme remnants, the universe is constantly in motion, constantly transforming. Supernovae are not just ends, they are powerful engines of change, enriching the cosmic environment and ensuring that the grand cycle of matter, energy, and creation continues. They are the ultimate testament to the universe's ability to self-renew, taking the destruction of one grand object to seed the birth of countless new possibilities. Imagine floating far above a vast spiral galaxy, watching it slowly spin like a colossal cosmic pinwheel. This isn't just a collection of stars, it's a dynamic ecosystem, constantly being shaped by the events within it. Supernovae play an absolutely crucial role in the evolution of these immense stellar islands. When a massive star explodes, it doesn't just enrich the immediate neighborhood. The powerful shockwave can actually blow vast bubbles in the interstellar gas, creating huge cavities within the galaxy's disk. These are like cosmic pressure cookers, pushing gas and dust around, sometimes compressing it enough to trigger new waves of star formation in distant regions. It's a bit like a cosmic stirring spoon, constantly churning the ingredients of the galaxy. In some cases, especially in smaller galaxies or regions with many supernovae occurring close together, the combined force of these explosions can be so powerful that they create galactic winds. Imagine immense plumes of gas and dust being blown right out of the galaxy, carrying newly forged elements into the vast emptiness of intergalactic space. It's like a cosmic geyser, blasting material into the void. This process is vital because it regulates how quickly new stars can form in a galaxy and helps explain why some galaxies appear red and dead, having used up or expelled much of their star-forming gas. Supernovae are, therefore, not just shaping their immediate surroundings, they are influencing the very destiny of entire galaxies. We briefly touched on Type Ia supernovae being like cosmic standard light bulbs. Let's delve a little deeper into just how powerful and indispensable they are for understanding the largest scales of the universe. Because these particular supernovae always explode with almost the same peak brightness, astronomers can use them as incredibly precise measuring tools. Imagine having a collection of light bulbs, but you know that every single one of them is exactly 100 watts, no matter what. If you then see one of these bulbs far away, and it looks dim, you can accurately calculate how far away it must be. This is exactly what astronomers do with Type Ia supernovae. They find them in distant galaxies, measure how bright they appear to be, and then, knowing their true brightness, they can calculate the immense distances to those galaxies. This isn't just a parlor trick, it's how we've mapped out the vast, expanding universe. It's how we discovered that the universe's expansion isn't slowing down, as we once thought, but is actually accelerating. This astonishing discovery led to the concept of dark energy, a mysterious force that seems to be pushing the universe apart. Without the consistent, powerful glow of Type Ia supernovae, we might never have uncovered this profound secret of the cosmos. They are truly the universe's ultimate cosmic rulers, allowing us to stretch our understanding to the very edge of the observable cosmos. So, supernovae are not just isolated events, they are critical components in the grand cosmic symphony. They recycle the material for new stars and planets. They sculpt the very structure of galaxies, blowing winds and stirring gas. And they serve as invaluable cosmic signposts that allow us to probe the most profound mysteries of the expanding universe. Every flash, every boom, every expanding bubble of gas contributes to the ongoing, dynamic, and ever-evolving story of the cosmos, a story in which we are all, ultimately, made of stardust. Imagine stretching your perception across billions of years, witnessing a galaxy not just as a static picture, but as a vibrant living entity. Over cosmic timescales, a galaxy is a continuous landscape of stellar births and deaths. Here, a new star ignites in a swirling cloud of gas. There, a mature sun shines steadily for eons. And then, somewhere else, a massive star reaches its dramatic end, blasting out its contents in a supernova. If you could speed up time, watching this cosmic dance, you would see flashes of light erupting across the galactic disk, like tiny, brilliant sparks in a colossal engine. Each flash marks the death of an old star and the scattering of the ingredients for new beginnings. These repeated supernova events mean that the entire universe, over its immense history, has become increasingly enriched with heavier elements. When the universe was very young, just after the Big Bang, it was almost entirely made of the lightest elements, hydrogen and helium. There was no carbon for life, no oxygen for water, no silicon for rocky planets, no iron for stars like our sun to make their cores. But the very first stars, truly massive pioneers born from these pristine, simple clouds, lived short, incredibly intense lives. They cooked up the first batches of heavy elements, and then, in their own powerful supernova explosions, they dispersed these vital ingredients into the early universe. These were the population 3 stars, a theoretical generation of stars we haven't directly observed yet, but know must have existed. Imagine them, giant, blazing blue-white suns, perhaps hundreds of times more massive than our own. Their supernovae would have been even more energetic and violent than the ones we typically see today, ripping apart their initial, pure hydrogen and helium forms and spreading the very first seeds of carbon, oxygen, and other heavier elements. It was these primordial explosions that laid the chemical foundation for everything that came later, including stars like our Sun and planets like Earth. Without these initial, ancient supernovae, the universe would remain a barren, lifeless place of simple gases. As time marched on, and more generations of stars lived and died, the cosmic recipe grew richer. Each supernova added its unique contribution to the growing cosmic inventory of elements. This process of enrichment is still happening today, constantly. The material from an exploding star might travel for millions of years before it eventually becomes part of a new star-forming cloud, perhaps many light years away from where it was first born. It's a slow, majestic circulation of matter, driven by the ultimate stellar fires. This steady, ongoing enrichment means that the composition of stars and the planets around them has changed over cosmic time. Younger stars, like our Sun, have a higher proportion of heavier elements compared to older stars. We can actually tell how metal-rich a star is by analyzing its light. This gives us clues about its age and how many generations of supernovae contributed to its birth cloud. It's like looking at the ingredients list of a cosmic dish and knowing how many times it's been remade and refined. So, supernovae are not just isolated, fleeting flashes of light. They are the engines of cosmic evolution, fundamental to the chemical composition of the universe. They sculpted the very earliest galaxies, provided the ingredients for the diverse stellar populations we see today, and continue to seed the cosmos with the promise of new worlds and new possibilities, endlessly renewing the grand cosmic cycle. Imagine for a moment that we could zoom out even further, beyond individual galaxies, to see the vast filamentary structure of the entire universe. Galaxies are not just randomly scattered. They form immense, intricate networks, like a cosmic web, with vast empty spaces called voids between them. Supernovae, of course, happen within galaxies, along the luminous strands of this web. They are the constant, brilliant explosions happening throughout these cosmic cities, punctuating the silence with their powerful flashes. The most spectacular supernovae, those from the collapse of massive stars, are truly a demonstration of the universe's principle of live fast, die young. Unlike the leisurely, billions of years life of a star like our Sun, these giants burn through their fuel in a cosmic blink of an eye. Their immense mass creates such incredible pressure and heat in their cores that fusion reactions race through their cycles at breakneck speeds. It's like a colossal engine running on overdrive, consuming its fuel at a voracious rate. This short, intense existence culminates in the dramatic iron core collapse, setting off the supernova. It's a life lived on the edge, constantly battling against overwhelming gravity until that final, inevitable moment of truth. Observing these explosive events can be a real challenge for astronomers. Many supernovae occur in distant galaxies, so far away that their light has traveled for millions or even billions of years to reach us. Sometimes, they are hidden behind thick clouds of dust and gas within their host galaxies, making them hard to spot in visible light. This is where our ability to see the universe in different kinds of light becomes absolutely crucial. Imagine if you were looking for a light bulb hidden behind a thick fog. You might not see its visible light, but if it's hot enough, you might feel its warmth, or detect it using special infrared goggles. Astronomers use powerful X-ray telescopes and gamma-ray telescopes orbiting high above Earth's atmosphere to pierce through this cosmic dust. When a supernova explodes, especially a core collapse one, it sends out a torrent of high-energy X-rays and gamma rays, which are much better at penetrating dust than visible light. So, even if a supernova is optically obscured, these energetic forms of light can reveal its presence, giving us a more complete census of these cosmic explosions. It's like having multiple pairs of cosmic eyeglasses, each revealing a different hidden layer of the universe. And what about trying to predict when and where a star might go supernova? That's incredibly difficult, almost like predicting the exact moment a volcano will erupt. Stars give off subtle clues as they near their end. Massive stars, for instance, often become incredibly large and cool red supergiants, like the star Betelgeuse we discussed. They might show slight variations in their brightness as their outer layers pulsate and shed material. Astronomers meticulously observe these stars, looking for any changes that might hint at an impending collapse. It's a bit like a cosmic vigil, patiently watching these giants, waiting for that telltale sign that their dramatic final act is about to begin. The amount of energy released in a supernova is truly staggering. For a few weeks, a single supernova can radiate as much energy as our Sun will emit over its entire 10 billion year lifetime. That's a mind-boggling amount of power, condensed into a fleeting moment. Imagine being able to harness even a tiny fraction of that raw cosmic energy. It's a profound demonstration of the universe's inherent power, a constant reminder of the scale and force at play in the cosmos. And as this energy disperses and the elements scatter, the relentless cycle continues, forever shaping the universe into the wondrous, complex place we inhabit and continually explore. We briefly touched upon those ghostly little particles called neutrinos, which flood out of a supernova at the moment of core collapse. It's worth pausing to appreciate just how incredible it is that we can actually feel these tiny messengers from across the universe. Imagine trying to catch a whisper from a distant galaxy. Neutrinos are even harder to detect. They barely interact with anything, passing straight through planets, stars, and even you, in countless billions every second. But when a massive star's core implodes to become a neutron star, it releases a colossal, truly enormous burst of neutrinos, a wave so intense that even our incredibly sensitive detectors here can pick up a few of them. One of the most famous examples of this happened in 1987. A supernova exploded in a nearby galaxy called the Large Magellanic Cloud, close enough for us to see with the naked eye. And just hours before its light reached us, a tiny handful of neutrinos arrived here on Earth, detected by underground observatories. Imagine that. These tiny particles, traveling almost at the speed of light, carrying news of a star's death hours before its light could make the journey. It was a profound moment for science, a direct confirmation of our theories about how these core collapse supernovae work. It's like hearing the footsteps of a giant, long before you see the giant itself. It gives us a window into the very heart of the explosion, right at the moment the core collapses. And pushing our perception even further, we are now entering a new era of listening to the universe through gravitational waves. Remember those ripples in the fabric of space-time, like ripples on a cosmic pond? These are incredibly subtle, but the most violent cosmic events, like the final collapse of a star's core into a neutron star or a black hole, should produce them. Powerful observatories here are specifically designed to detect these minuscule distortions in space-time. While we haven't yet directly detected gravitational waves from a core collapse supernova, it's only a matter of time. Imagine being able to not just see the flash of a supernova, but to feel the very space around you subtly stretching and squeezing as the cosmic tremor passes through. It would be like a profound, silent roar from across the universe, giving us yet another way to witness these magnificent events. While we've mostly focused on the two main types of supernovae, core collapse from massive stars and type Ia from white dwarfs, the universe always has surprises. There are even rarer, more exotic kinds of stellar explosions. For instance, some truly gigantic stars so massive they are hundreds of times the mass of our Sun, might end their lives in a different kind of explosion called a pair instability supernova. In these cases, the star gets so hot that pure energy, in the form of gamma rays, starts spontaneously converting into pairs of particles and antiparticles, which actually robs the star of its internal pressure. This causes a sudden, runaway collapse, and then an explosion that might be even more powerful than a regular supernova, completely obliterating the star and leaving no compact remnant behind. These were probably more common in the very early universe, contributing to that initial cosmic enrichment. It shows us that even within the category of supernova, there's a dazzling variety of cosmic violence. All these different types, from the quiet accretion of a white dwarf's companion to the cataclysmic collapse of a supergiant, underscore the central role of supernovae in the grand cosmic narrative. They are the great element factories and dispersers, the cosmic reset button that takes old matter and reshapes it for new beginnings. Without them, the elements that make up planets, oceans, atmospheres, and indeed, every living thing would simply not exist in the quantities needed to form complex structures. So, when you look up at the night sky, remember that every point of light, every star, carries the potential for a supernova, and every part of you carries the legacy of one. Imagine yourself floating out there, far beyond our galaxy, looking back at it. From this immense distance, individual stars would be impossible to distinguish. But when a supernova flares up, it's like a single, brilliant flashbulb going off in a cosmic city of billions of lights. These brief, intense flashes act as powerful beacons, lighting up the darkness and giving us unique opportunities to study very distant galaxies. They are like cosmic lighthouses, their brilliant light traveling across unimaginable stretches of space and time to reach our telescopes. Because of their extreme brightness, especially the type Ia supernovae with their remarkably consistent peak luminosity, we can see them even in galaxies that are billions of light years away. This allows us to probe the most distant reaches of the observable universe. Imagine using these cosmic flashes to map out the grand architecture of the cosmos, seeing how galaxies are distributed and how fast they are moving away from each other. It's through studying these distant supernovae that we confirmed the astonishing discovery that the universe's expansion isn't slowing down, but actually speeding up, driven by that mysterious force we call dark energy. Without these brilliant, fleeting signposts, we would have a far less clear picture of the universe's ultimate fate and its accelerating expansion. They are not just stellar deaths, they are cosmic keys, unlocking fundamental secrets about the very fabric of space and time. These explosive stellar deaths are also vital for the ongoing evolution of galaxies themselves. Think of a young galaxy, brimming with fresh gas and dust, constantly forming new stars. The most massive of these new stars quickly live out their short, brilliant lives and then explode as supernovae. These explosions are incredibly disruptive, but in a good way for the galaxy. The shockwaves they send out are like cosmic plows, churning up the gas and dust, heating it, and preventing it from simply settling into a static, unchanging state. This stirring action is crucial. It helps to regulate the rate at which new stars form, sometimes triggering new star birth by compressing gas clouds, and sometimes dispersing gas, slowing down star formation in certain regions. The long-term legacy of a supernova remnant is just as important as its initial dazzling flash. Imagine watching that vast bubble of superheated gas and dust, still slowly expanding outward, sweeping up interstellar material as it goes. Over millions of years, these remnants fade, cool, and eventually merge back into the general interstellar medium. The elements they have scattered, those precious atoms forged in stellar cores, and during the explosion itself, become thoroughly mixed into the galaxy's gas. This continuous enrichment means that each successive generation of stars, and the planets that form around them, will be richer in heavy elements than the last. This gradual increase in heavier elements over cosmic time is a silent but profound testament to the tireless work of supernovae. It means that planets capable of supporting complex chemistry, like our own rocky world, become more common as the universe ages. It is a slow, majestic, and ongoing process, driven by the most violent events imaginable. The cycle of star birth, stellar life, supernova death, and cosmic recycling is fundamental to the universe's evolution. It ensures that the raw ingredients for complexity are always available, always replenished, constantly setting the stage for new cosmic wonders, perhaps even new forms of life, to emerge in the vastness of space. It ensures that the raw ingredients for complexity are always available, always replenished, constantly setting the stage for new cosmic wonders, perhaps even new forms of life, to emerge in the vastness of space. Imagine continuing our drift, now pulling back to see not just single galaxies, but entire clusters of them, stretching across the colossal cosmic web. This web, that vast, intricate network of filaments and voids, is the largest structure in the universe. And within these luminous threads of galaxies, supernovae are constantly flashing, like tiny, brilliant sparks. These explosions, though localized, contribute to the grand cosmic churn, influencing the gas and plasma that fills the space between galaxies in these clusters. Their energy can heat this intergalactic gas, affecting how galaxies within the cluster interact and grow. It's a testament to the idea that even seemingly small, individual events can have ripple effects across truly enormous cosmic distances. The very rapid life and dramatic death of those massive stars that give rise to the most common type of supernova is a critical driver of this cosmic dynamism. Because they burn so brightly and die so quickly, they inject tremendous amounts of energy and newly forged elements into their surroundings in a very short cosmic time frame. This constant, furious energy input acts like a galactic thermostat, helping to regulate the temperature of the gas within a galaxy and in the spaces between galaxies and clusters. It prevents gas from simply cooling down too quickly and forming too many stars all at once, leading to a more regulated, extended period of star formation throughout cosmic history. Without these powerful, recurring blasts, galaxies would look very different, perhaps exhausting their star-forming fuel much faster. This ceaseless cosmic activity, powered by supernovae, means that the universe is never truly static. It's always evolving, always refining its composition. The elements created in supernovae are not just scattered, they are beautifully integrated into the cosmic tapestry. They become part of the vast molecular clouds where new stars are born. Sometimes, the shock wave from an old supernova remnant will actually crash into one of these existing clouds of gas, compressing it, making it dense enough to finally collapse under its own gravity and kickstart a new generation of stars. It's like a cosmic domino effect, where one stellar death triggers a wave of new stellar births. From our vantage point, looking back through cosmic time, supernovae serve as crucial historical markers. The chemical composition of stars and galaxies, detected through their light, tells us a story. By studying how the proportion of heavy elements changes in very old galaxies versus younger ones, we can trace the history of star formation and supernova activity across the entire universe. It's like reading the universe's chemical diary, with each entry telling us about the intense, fiery work done by supernovae throughout the eons. The amount of iron, for example, in distant galaxies, is a direct indicator of how many massive stars lived and died there in the past. These cosmic explosions, though moments of violent destruction, are fundamental to the universe's ongoing story of creation. They remind us that chaos can lead to order, and death can be a necessary prelude to new life. They are the ultimate testament to the universe's ability to renew itself, to continually build complexity from simplicity, and to paint the cosmos with ever more vibrant and intricate patterns. This ceaseless cosmic activity, powered by supernovae, means that the universe is never truly static. It's always evolving, always refining its composition. The elements created in supernovae are not just scattered, they are beautifully integrated into the cosmic tapestry. They become part of the vast molecular clouds where new stars are born. Sometimes, the shock wave from an old supernova remnant will actually crash into one of these existing clouds of gas, compressing it, making it dense enough to finally collapse under its own gravity and kickstart a new generation of stars. It's like a cosmic domino effect, where one stellar death triggers a wave of new stellar births. From our vantage point, looking back through cosmic time, supernovae serve as crucial historical markers. The chemical composition of stars and galaxies, detected through their light, tells us a story. By studying how the proportion of heavy elements changes in very old galaxies versus younger ones, we can trace the history of star formation and supernova activity across the entire universe. It's like reading the universe's chemical diary, with each entry telling us about the intense, fiery work done by supernovae throughout the eons. The amount of iron, for example, in distant galaxies, is a direct indicator of how many massive stars lived and died there in the past. These cosmic explosions, though moments of violent destruction, are fundamental to the universe's ongoing story of creation. They remind us that chaos can lead to order, and death can be a necessary prelude to new life. They are the ultimate testament to the universe's ability to renew itself, to continually build complexity from simplicity, and to paint the cosmos with ever more vibrant and intricate patterns. Now, let's consider another powerful yet often unseen legacy of supernovae: cosmic rays. These aren't the gentle rays of light or heat we often talk about. Imagine incredibly tiny, high-speed particles, mostly atomic nuclei, stripped of their electrons, zipping through space at nearly the speed of light. These cosmic bullets originate from the most violent events in the universe, and supernovae, specifically their expanding remnants, are thought to be the primary accelerators. As the shockwave from an exploding star slams into the surrounding interstellar gas, it creates a powerful magnetic turbulence. Within this cosmic chaos, charged particles are repeatedly bounced back and forth, gaining enormous amounts of energy with each bounce, until they are flung out into space as cosmic rays. These energetic particles travel across galaxies, constantly bombarding everything in their path. While we are mostly protected by a planet's atmosphere and magnetic field, cosmic rays play a role in the chemistry of interstellar clouds and even slightly affect the radiation environment in space. It's yet another way a supernova, millions of years after its initial blast, continues to influence the cosmos, spreading not just matter, but also immense amounts of kinetic energy in the form of these incredibly fast-moving particles. And speaking of extreme energy, some supernovae give rise to the most powerful explosions in the entire universe, gamma-ray bursts, or GRBs. These are incredibly brief yet unbelievably intense flashes of gamma rays, the highest energy form of light. A single GRB can emit more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. Imagine that concentrated power. It's truly mind-boggling. Most long-duration gamma-ray bursts, which last longer than a couple of seconds, are now understood to be connected to the collapse of very specific, extremely massive stars. These aren't just any large stars. They are believed to be massive stars that are also spinning incredibly rapidly and have shed most of their outer hydrogen layers. When such a star exhausts its nuclear fuel and its core collapses, instead of a symmetrical explosion, the energy is focused into two incredibly powerful, narrow jets of material that blast out from its poles at nearly the speed of light. It's like a cosmic cannon firing pure energy. If one of these narrow jets happens to be pointed directly at us across billions of light-years of space, we detect it as a gamma-ray burst. It's an almost unimaginable burst of raw power, a fleeting, bright scream from the very edge of the observable universe. Detecting these gamma-ray bursts is a challenge because they are so short-lived. Space telescopes constantly monitor the sky for these flashes. Once a GRB is detected, astronomers quickly try to find its afterglow in other wavelengths, like X-ray, visible light, and radio, to pinpoint its exact location and study the distant galaxy it came from. These observations provide crucial clues about the most massive stars, the conditions in the very early universe, and how black holes form. It's like catching a fleeting glimpse of the universe's most extreme, violent, yet ultimately revealing moments. And after all this incredible energy, after the cosmic fireworks and the powerful blasts of particles and jets, the supernova's light begins its long, slow fade. It's not an immediate extinguishing. For weeks, then months, the brilliant glow gradually diminishes. By carefully measuring how the light changes over time, what we call a light curve, astronomers can learn even more about the explosion. The shape and speed of the fading light tell us about the type of supernova, the mass of the exploding star, and the elements produced in the blast. It's like watching a cosmic ember slowly cool, but even as it dims, it continues to whisper secrets about its dramatic final act. Now, as that brilliant light recedes into memory, the supernova remnant continues its immense, unhurried expansion. Imagine it now, not as a flash, but as a colossal, intricate bubble of gas and dust, still glowing from the energy of the explosion, but also from the friction as it pushes through the thin interstellar medium. These cosmic bubbles can grow to truly enormous sizes, spanning hundreds of light-years across. We've seen many of them, beautiful and complex structures like the famous Veil Nebula or the still expanding shell of supernova 1987A, the one that gave us those precious neutrinos. Over thousands and tens of thousands of years, these remnants will continue to expand. The glowing filaments will become more stretched and diffuse. The initial superheated gas will slowly cool down. Eventually, after millions of years, the once spectacular nebula will have faded completely, its material dispersed so widely that it simply blends into the general interstellar gas of the galaxy. It's a very slow, majestic dissolution, a cosmic fading from glory, but one that is absolutely essential for the universe's ongoing cycle. Because this dispersed material, enriched with all those precious heavy elements forged in the star's life and death, doesn't just vanish. It becomes part of the vast, diffuse interstellar medium, the cosmic soup between the stars. Imagine a galaxy as a giant, recycling plant, and supernovae are the key machines that break down old, massive components and redistribute their valuable parts. These shockwaves from supernovae, as they expand and interact with existing gas clouds, can actually compress them, making them denser and colder. This compression can trigger new waves of star formation. So, the death of one star is often the direct catalyst for the birth of an entirely new generation of stars and, crucially, their accompanying planetary systems. It's a truly profound connection. Almost all the elements heavier than hydrogen and helium, everything from the silicon in rocks to the calcium in your bones, the iron in your blood, and even the gold and silver we value, owe their existence to the processes within stars and the violent, incredible power of supernovae. Without these colossal explosions, the universe would still be a very simple place, just vast clouds of the lightest elements, hydrogen and helium, with no rocky planets, no complex chemistry, and certainly no life as we understand it. Supernovae are the universe's way of ensuring that there's enough cosmic grit for interesting things to happen. We can even see the echoes of ancient supernovae in our own galactic neighborhood. There are vast bubbles and cavities in the interstellar gas around us, regions where the gas is much thinner than average. These are thought to be the remnants of past supernovae that occurred relatively close to our solar system over millions of years, carving out these immense voids. It's like finding the subtle, long-faded splash marks from a giant cosmic pebble thrown into the galactic pond countless eons ago, still detectable today. This history of stellar explosions has directly influenced the distribution of gas and dust in our own corner of the galaxy, shaping the very environment in which our sun and planets eventually formed. So, supernovae are not isolated, rare curiosities. They are deeply, intrinsically woven into the fabric of cosmic evolution. They are the grand architects of galactic structure, the primary sources of the elements that build planets and life, and the powerful engines that drive the continuous cycle of creation and recreation in the universe. Every distant flash, Every expanding remnant, every whisper of a neutrino reminds us of the universe's relentless dynamism, its unending capacity for both spectacular destruction and breathtaking renewal. Imagine now stretching your mind not just across space, but across time itself. When we observe a supernova in a galaxy that is millions or even billions of light years away, we are actually looking back in time. The light we see left that exploding star millions or billions of years ago, long before our own planet even formed. So, each distant supernova is like a cosmic time capsule, delivering information about the universe as it was in a much younger state. By studying supernovae at different distances, and thus at different moments in the universe's past, we can piece together a grand cosmic timeline, seeing how galaxies formed and evolved, and how the rate of star formation, and therefore supernova activity, has changed over eons. In the early universe, when galaxies were just beginning to form, starbirth was much more frantic and widespread than it is today. This means that supernovae were also much more frequent. Imagine the early cosmos, a much more violent and active place, with colossal explosions lighting up the young galaxies far more often than they do now. As the universe aged, and much of the free gas was used up in star formation, the rate of new star births has gradually slowed down, and with it, the frequency of supernovae. So, in a sense, the universe is slowly becoming a quieter place, though still punctuated by these spectacular events. These cosmic explosions are also intimately linked to the story of cosmic dust. Dust in space isn't like the dust bunnies under your furniture. It's made of tiny, microscopic solid particles, often complex carbon molecules or silicates, like tiny grains of cosmic sand. This dust is absolutely vital for making planets. Without dust, you can't build rocks, and without rocks, you can't build planets. Supernovae play a dual role here. They create a significant amount of dust in their powerful explosions and expanding remnants, as newly formed heavy elements condense into solid grains in the cooler, outer parts of the ejector. But their powerful shockwaves can also destroy existing dust by slamming into it and pulverizing the tiny grains. It's a constant cosmic dance of creation and destruction, ensuring that dust is continually recycled and redistributed throughout galaxies, making sure that future planet formation has enough raw material. The ongoing study of supernovae is one of the most exciting frontiers in astronomy. Despite all we've learned, there are still many profound mysteries that keep scientists eagerly searching the skies. For instance, while we understand the general mechanics, the exact details of how a massive star's core collapses and sends out that powerful shockwave, and how it manages to avoid fizzling out, are incredibly complex and still being refined. It's like understanding how a car works in general, but trying to pinpoint every single tiny gear and spring in a microscopic explosion happening in milliseconds. We're still trying to understand the precise conditions that lead to those powerful gamma-ray bursts, distinguishing between the types of massive stars that produce them and those that just explode in a more standard way. Every new supernova observed, whether it's a nearby flash or a faint shimmer from billions of light years away, adds another piece to this grand cosmic puzzle. It allows us to test our theories, refine our models, and push the boundaries of our understanding. It's a journey of continuous discovery, where each brilliant stellar death unveils more secrets about the universe's past, its present, and its astonishing future. Imagine being part of that ongoing quest, where every new flash of light reveals a deeper layer of cosmic truth. To unlock these deeper layers of cosmic truth, astronomers rely on an incredible array of tools. Imagine a vast network of eyes, constantly scanning the heavens, each one designed to see a different part of the universe's vibrant light spectrum. Powerful ground-based telescopes, often perched on remote mountaintops under the clearest skies, are equipped with sophisticated cameras that can capture the sudden brightening of a distant supernova. These are often the first to spot the explosion, providing critical early data. But as we've discussed, not all of a supernova's secrets are revealed in visible light. So, we send robotic observatories into space. Space telescopes, orbiting high above the blurring effects of Earth's atmosphere, can capture the intense bursts of X-rays and gamma rays, those high-energy forms of light that signal the initial stages of a massive star's collapse or a powerful gamma-ray burst. They also see in ultraviolet and infrared light, piercing through cosmic dust clouds that would completely obscure a supernova's glow in visible wavelengths. It's like having a cosmic detective agency, with different specialists each looking for a particular clue, all working together to solve the mystery of these fleeting events. And it's not just professional astronomers who are part of this grand search. There's a wonderful community of citizen scientists, amateur astronomers with their own telescopes, who contribute to the hunt for supernovae. They often meticulously scan nearby galaxies, looking for any new, unexpected points of light. When they find one, they alert professional observatories, who then swing their giant instruments into action for detailed study. It's a beautiful example of how curiosity and dedication, even without immense resources, can contribute to humanity's collective understanding of the cosmos. Imagine being the first human to spot a new supernova, a flash that might be millions of light years away, announcing a stellar death that happened eons ago. Sometimes, the universe offers an even more astonishing way to study these distant explosions through a phenomenon called gravitational lensing. Remember that idea of space-time being like a flexible trampoline? Massive objects, like entire clusters of galaxies, create deep dips in this trampoline. When light from a very distant supernova travels towards us, and it happens to pass by one of these massive galaxy clusters, the cluster's gravity can bend and magnify the supernova's light, just like a cosmic magnifying glass. This can create multiple images of the same supernova, or make it appear much brighter than it actually is. Imagine seeing the same supernova flash, but in 2 or 3 slightly different places in the sky, each one a stretched or distorted view of the same event. This not only gives us a chance to study these incredibly distant, ancient supernovae in greater detail, but it also allows us to map out the distribution of mass in those foreground galaxy clusters, including the mysterious dark matter that makes up most of the universe's mass, but doesn't interact with light. These gravitationally lensed supernovae are incredibly rare, but when discovered, they provide an unparalleled window into the very early universe and its grandest structures. So, from the intricate workings of our telescopes to the dedicated eyes of citizen scientists, from the ghostly whispers of neutrinos to the cosmic magnifying power of gravity, our quest to understand supernovae is a relentless pursuit. Each new piece of information strengthens our cosmic story, revealing more about how these profound stellar deaths are intertwined with the birth of elements, the formation of galaxies, and the very unfolding of the universe's grand narrative. They are not just fleeting fireworks, they are continuous, powerful actors in the ongoing cosmic drama. Imagine the universe not just as a collection of static lights, but as a vast, ever-evolving ecosystem where the birth and death of stars play a pivotal role. The elements forged and dispersed by supernovae are not just scattered randomly. They become the building blocks for new generations of stars, and these generations have subtly different characteristics depending on the cosmic history of their birth cloud. The very first stars, those theoretical population 3 stars we discussed, were born from the pure, pristine hydrogen and helium left over from the Big Bang. They were massive, short-lived, and their supernovae were the universe's first factories for heavy elements. Imagine the immense, primordial silence broken by these first, furious explosions, seeding the cosmos with the very first carbon, oxygen, and iron. Then came the population 2 stars. These stars formed from gas that had been lightly enriched by the first supernovae. They contain fewer heavy elements than our Sun, but more than the population 3 stars. Many of these ancient, metal-poor stars can still be found today in the faint, sprawling halos around galaxies, silent witnesses to the universe's early, more chemically simple times. Their own deaths, if massive enough, continued the grand enrichment. And finally, there are stars like our Sun, which are population 1 stars. These are the younger, more chemically rich stars, born from gas and dust that has been repeatedly enriched by countless generations of supernovae. These stars have a higher proportion of those heavier elements, the ones necessary to form rocky planets, which in turn are essential for life as we know it. So every supernova, whether ancient or recent, is an essential step in this cosmic evolution, ensuring that the universe becomes progressively more complex and hospitable for phenomena like planets and living beings. It's a beautifully intricate cosmic dance, from pure gas to complex chemistry, all choreographed by stellar deaths. beyond the well-known types, the universe continues to surprise us with even more exotic forms of supernovae. For example, some stars, not quite massive enough to form an iron core but a bit larger than our Sun, can experience an electron capture supernova. In these cases, the core collapses not because it runs out of fusion fuel, but because its electrons are forced into the atomic nuclei by overwhelming gravity, removing the pressure that supported it. It's a subtle but fascinating difference in the final moments. And at the other end of the spectrum, there are incredibly rare, intensely powerful superluminous supernovae, which shine hundreds of times brighter than a typical supernova. The exact mechanism behind these super bright explosions is still a mystery, perhaps involving incredibly massive stars, or new physics we don't yet fully understand. They are like cosmic ultra-beacons, challenging our current theories and pushing us to explore the boundaries of stellar physics. Supernovae are also incredible cosmic laboratories. The extreme conditions during these explosions, temperatures hotter than the core of our Sun, pressures unimaginable, and densities beyond anything we can create on Earth, allow us to test the very limits of our understanding of physics. The way matter behaves under such crushing forces, the way light is generated and travels through the expanding debris, the subtle interactions of neutrinos and gravitational waves, all these phenomena offer unique insights into fundamental laws. It's like having a giant, natural particle accelerator in space, allowing us to probe the secrets of the universe's most basic building blocks. The quest to understand supernovae is far from over. Future generations of telescopes, both on the ground and in space, will offer even sharper eyes and ears to the cosmos. Imagine new gravitational wave detectors that can pinpoint a supernova's location with much greater accuracy, or neutrino observatories that can capture even more of those ghostly particles. These advancements promise to deepen our understanding of these cosmic titans, perhaps revealing new types of explosions, or shedding light on the elusive nature of black holes and neutron stars. Our journey of discovery through the universe is a continuous one, forever guided by the magnificent, powerful flashes of stellar death. Imagine now that we could trace every atom around us, every speck of dust, every drop of water, every molecule in our own bodies, back to its cosmic birthplace. You might be surprised to learn that almost everything you see, touch, and are has its roots in a star, and very often in a supernova. We've talked about how stars fuse light elements into heavier ones, like hydrogen into helium, then carbon, oxygen, and all the way up to iron. But that's not the whole story for all the elements on the periodic table. The truly heavy elements, the ones beyond iron, like gold, platinum, and uranium, require even more extreme conditions to form. While some are created in the violent shock waves of a core collapse supernova, a significant amount of these super-heavy elements are believed to be forged in an even rarer, and perhaps even more dramatic, cosmic event, the merger of two neutron stars. Think back to those incredibly dense remnants of massive stars that went supernova. A neutron star is like a cosmic zombie, dead but still incredibly powerful. Now, imagine two of these super-dense objects, each one packing more mass than our Sun, into a sphere just the size of a city, locked in a tight, gravitational dance around each other. These two neutron stars are the direct result of previous supernovae. They orbit each other closer and closer, spiraling inwards over immense spans of cosmic time, radiating away energy as gravitational waves. And then, after perhaps billions of years of this spiraling ballet, they finally collide. This isn't just an impact, it's an event of unimaginable violence and power, causing a phenomenon known as a kilonova. When these two neutron stars smash into each other, their combined mass and the immense forces involved create conditions so extreme that they fuse together, briefly. During this incredibly energetic merger, a tiny but crucial amount of matter is ejected at tremendous speeds, and within this outflow, the conditions are perfect for a rapid-fire process that builds those super-heavy elements. It's in this fleeting, cataclysmic moment that most of the gold and platinum in the universe is believed to be created. Imagine seeing that. Two stellar corpses, the remnants of ancient supernovae, colliding to form the very ingredients for our most prized metals. The light from a kilonova is far dimmer than a supernova, perhaps 1,000 times less bright, and fades much more quickly. But it shines brightest in infrared light, revealing the glow of these newly forged heavy elements. We've actually observed one such event, picking up both its gravitational waves and its light, and confirming our theories about how gold is made in the universe. It's like finding the universe's ultimate goldsmith in a cosmic forge fueled by the aftermath of two stellar deaths. So, when you consider the intricate dance of elements, from the hydrogen forged in the Big Bang to the iron made in massive stars, and the gold created in neutron star mergers, you start to see the profound interconnectedness of everything. Supernovae, both directly and indirectly through their neutron star remnants, are the cosmic architects that have built the chemical diversity of the universe. They are the reason we have rocky planets, and oceans, and the very complex chemistry that allows for life. Every breath you take, every bite of food, every sensation you feel, is fundamentally linked to these immense, powerful, and beautiful stellar deaths. We are, quite literally, creatures of the stars, made from the ashes and the energy of long-dead suns. It's a story written in the very atoms that compose us, a silent testament to the enduring power and relentless creativity of the cosmos. As the universe continues its grand, unending journey, stars will continue to be born, live their lives, and eventually explode, forever ensuring that the cosmic canvas is repainted with new elements, new possibilities, and new wonders. The grand cosmic ballet of creation and destruction continues endlessly. Imagine now that you could trace the paths of individual atoms, watching them flow through the universe. An atom of oxygen, perhaps, born in the core of a massive star, blasted out in a supernova, then drifting through interstellar space for millions of years. It might then be swept up into a new cloud of gas and dust, eventually finding its way into a swirling disk around a new star, condensing to become part of a rocky planet. And perhaps, billions of years later, that very atom of oxygen could become part of an ocean, or an atmosphere, or even part of a living being. This isn't just poetic thought, it's the very real, physical journey of matter in the cosmos, a cycle that supernovae are absolutely central to. They are the cosmic alchemists, constantly transforming raw material and distributing it for new uses. Our own little corner of the galaxy, the space surrounding our solar system, actually bears the indelible marks of past supernova events. Scientists have found evidence for what's called the local bubble. Imagine an immense, irregular cavity, perhaps 1,000 light-years across, in the interstellar gas around us. This bubble is a region where the gas is much hotter and thinner than the surrounding interstellar medium. The leading theory is that this local bubble was created by a series of powerful supernovae that exploded relatively close to us over the last few million years. These ancient explosions effectively blew huge holes in the galaxy's gas, clearing out vast regions and pushing matter into denser walls around the bubble. This history of local supernovae might even have played a role in the formation of our own sun and its planets. The shockwaves from these past explosions could have compressed nearby gas clouds, triggering the very collapse that led to the birth of our solar system. Or perhaps, they simply helped to shape the interstellar environment in which our solar system peacefully developed. It's a fascinating thought, isn't it? That the very space we inhabit, the relatively clear cosmic highway on which our sun travels, might be a direct legacy of stellar explosions that occurred eons ago, far before humanity ever dreamed of looking up at the stars. The future of supernova research promises even more astonishing revelations. New generations of telescopes, both on Earth and in orbit, are being designed to see deeper into space and across more wavelengths of light than ever before. Imagine giant arrays of radio telescopes that can pick up the faint radio waves from ancient supernova remnants, revealing their structures in unprecedented detail. Or incredibly sensitive X-ray observatories that can precisely map the distribution of elements blown out by a supernova, telling us exactly where and how they were formed. Even more exciting, the ongoing development of neutrino detectors and gravitational wave observatories holds the key to unlocking even deeper secrets. Imagine being able to pinpoint the exact moment of a star's core collapse, to hear the cosmic rumble of gravitational waves from an exploding star as clearly as you see its light. This multi-messenger astronomy, combining light, neutrinos, and gravitational waves, gives us a truly holistic understanding of these extreme events. like listening to a cosmic orchestra with every instrument perfectly tuned. It promises to reveal the fine-grained details of supernova physics that are currently beyond our grasp. These powerful stellar deaths, while relatively rare for any single star, are constant and vital forces, shaping the cosmos on every scale. From the smallest atom to the largest galactic structure, their influence is undeniable. They are the dynamic force that ensures the universe is not just a static collection of stars, but a vibrant, evolving tapestry, constantly being repainted with new colors, new materials, and new possibilities, all driven by the awe-inspiring power of the supernova. Imagine now floating just beyond a magnificent swirling spiral galaxy. You're not seeing it as a static picture, but as a living, breathing entity, constantly churning and evolving. Within this cosmic dance, the remnants of past supernovae play a crucial role, not just by scattering elements, but by literally sculpting the interstellar landscape. The immense shockwaves from these explosions act like colossal cosmic snowplows, sweeping up existing gas and dust. This creates vast, intricate structures, immense bubbles of thin, hot gas, surrounded by denser, cooler shells. These shells, compressed by the force of the supernova blast, can become incredibly dense, and it's in these dense regions that the conditions become just right for new stars to ignite. So, the death of one star directly carves out space and compresses the raw material for the birth of many more. It's a beautiful, dynamic interplay of destruction and creation. You can almost see the echoes of these ancient blasts in the shapes of some of the most beautiful nebulae we observe, those glowing clouds of gas and dust that look like cosmic sculptures. They are often carved by the very powerful winds and explosions of massive stars that lived and died within them. And what about those incredibly dense objects left behind after a massive star's core collapses? The neutron stars and black holes are the ultimate, compact legacies of supernovae. Imagine a neutron star just miles across, spinning hundreds of times a second, its surface so dense that a drop of water would weigh more than every car on Earth combined. These extreme objects, born from fire, continue their cosmic journey, sometimes leading to even more dramatic events like the kilinovae we discussed, when two of them merge. Then there are the black holes, those enigmatic regions where gravity is so intense that nothing escapes. These cosmic voids are not just static holes, they are constantly interacting with their surroundings. If a black hole happens to be orbiting a normal star, it can slowly pull gas from its companion, forming a superheated, swirling disk of material that spirals inwards. As this gas gets closer and closer to the black hole's edge, it gets incredibly hot and glows brightly in X-rays, allowing us to detect the black hole's invisible presence. It's like watching a cosmic whirlpool, where matter performs a fiery dance before disappearing forever into the unknown. The elements forged and dispersed by supernovae are not just random cosmic ingredients. They are the fundamental building blocks that allow for the incredible diversity of planetary systems we are now discovering across the galaxy. From gas giants to icy worlds, from rocky planets like our own to potential ocean worlds rich in water, each planet's composition is a direct result of the specific mix of elements available in its birth cloud. And that mix, in turn, is a direct consequence of the supernova history of its galactic neighborhood. It's a profound thought. The type of planet that forms, and therefore the potential for different kinds of life, is intrinsically linked to the violent stellar deaths that came before. Despite the fact that a supernova in our own galaxy is a rare sight for a human lifetime, their cumulative effect across billions of years and billions of galaxies is monumental. They are the engine of cosmic chemistry, the sculptors of galactic landscapes, and the indispensable architects of complexity. Every time we observe a new supernova, or study the fading glow of an old remnant, we are deepening our understanding of the universe's grand design, its endless capacity for transformation, and our own profound connection to the fiery heart of creation. Imagine reaching out your hand into the cosmic darkness, grasping for something to give you a sense of scale, a way to measure the immense distances between galaxies. For astronomers, supernovae, especially the Type Ia variety, serve as those indispensable cosmic yardsticks. Because they explode with such a consistent brightness, they are like powerful, perfectly calibrated light bulbs scattered throughout the universe. By measuring how dim one of these cosmic light bulbs appears, we can precisely calculate its distance. This isn't just about drawing a map, it's about understanding the very fabric of expanding space. It was by painstakingly observing these distant Type Ia supernovae that scientists made the astonishing discovery that the universe's expansion is actually accelerating. Before these observations, the common thought was that gravity from all the matter in the universe would gradually slow down its expansion. But the supernovae told a different story. Galaxies were rushing away from each other faster and faster. This led to the concept of dark energy, a mysterious force that seems to be pushing space itself apart. Without the consistent, brilliant flash of supernovae, we would still be largely in the dark about this fundamental property of our cosmos. They are truly the universe's most reliable witnesses to its own grand, accelerating destiny. Not all supernovae announce themselves with a brilliant, easily visible flash. Some, especially those occurring deep within dusty spiral arms of galaxies, can be obscured by thick clouds of interstellar dust. Imagine trying to see a bright flashlight beam through a dense fog. The light simply gets scattered and absorbed. This is why astronomers can't rely solely on visible light. We must employ our full spectrum of cosmic senses. Infrared telescopes can peer through these dusty veils, as infrared light is much less affected by dust. So, a supernova that might be completely hidden in visible light can shine brightly in the infrared, revealing its presence. Similarly, the very earliest moments of a massive star's collapse, particularly the core collapse supernovae, often send out tremendous bursts of X-rays and gamma rays. These high-energy forms of light can pierce through obscuring material, providing early warnings and unique insights into the physics of the explosion. It's like having a cosmic X-ray vision, allowing us to see through the murkiness and catch every type of stellar demise, ensuring we don't miss any of the universe's grand, destructive, and creative events. As we continue to observe the universe, we see that supernovae are not evenly distributed. They occur most frequently in spiral galaxies and in regions of active star formation, which are often found in the colossal filaments of the cosmic web. In merging galaxies, where immense gas clouds collide and new stars are born in frenzied bursts, the rate of supernovae can skyrocket. Imagine two vast cosmic cities smashing together, creating a firestorm of new star births, each one with the potential for a spectacular, element-spreading death. These galactic collisions become cosmic fireworks displays, fueled by an accelerated rate of stellar explosions. While the odds of a supernova happening very close to our own solar system are incredibly low, across the vastness of the observable universe, these events are happening constantly. Every second, somewhere in the cosmos, a star is meeting its end in a blinding, element-generating explosion. These continuous flashes, each one a unique cosmic event, are collectively responsible for shaping the galaxies, enriching the interstellar medium, and setting the stage for new stars, new planets, and new possibilities. They are the universe's tireless engines of change, forever reminding us of the dynamic, ever-evolving nature of our cosmic home. These powerful stellar deaths, while relatively rare for any single star, are constant and vital forces, shaping the cosmos on every scale. From the smallest atom to the largest galactic structure, their influence is undeniable. They are the dynamic force that ensures the universe is not just a static collection of stars, but a vibrant, evolving tapestry, constantly being repainted with new colors, new materials, and new possibilities, all driven by the awe-inspiring power of the supernova. As we continue our cosmic journey, letting our minds stretch across the vastness, one of the most remarkable things about supernovae is how they act as profound windows into the universe's past. When we observe a supernova in a galaxy that's, say, 1 billion light-years away, the light we are seeing left that star 1 billion years ago. That means we're not just seeing an explosion, we're seeing what the universe was like 1 billion years ago. It's like a natural time machine. By studying supernovae at different distances, we build a cosmic photo album of the universe at various stages of its development. We can see how galaxies were different, how stars were forming more actively, and how the very chemistry of the cosmos was less evolved. This time-traveling capability is crucial for understanding the universe's grand story. The light from incredibly distant supernovae is also stretched, or redshifted, by the expansion of space itself. Imagine a wave drawn on a rubber band. As the rubber band stretches, the wave gets longer. Similarly, As light travels across the expanding universe, its wavelengths get stretched, shifting towards the red end of the spectrum. By precisely measuring this redshift, astronomers can figure out just how much the universe has expanded since that supernova's light began its journey. This is another layer of information that helps us chart the universe's history and confirm its accelerating expansion, revealing the pervasive influence of dark energy. Supernovae also serve as incredible, naturally occurring laboratories for testing the most extreme physics. Imagine trying to recreate the conditions inside an exploding star here on Earth. It's simply impossible. The temperatures, pressures, and densities are far beyond anything we can achieve in our laboratories. But by studying the light, the neutrinos, and the potential gravitational waves from supernovae, we gain direct insight into how matter behaves under these incredible forces. This helps us refine our understanding of fundamental particles, the structure of atomic nuclei, and even the very nature of space and time. They offer unique glimpses into the extreme limits of physical laws, pushing the boundaries of human knowledge in ways no terrestrial experiment ever could. Even after their dazzling initial flash, the fading supernova remnants continue to be a rich source of information for thousands and millions of years. Imagine tracking one of these immense, expanding bubbles of gas and dust. Over time, the material cools, condenses, and eventually merges back into the vast interstellar medium, ready to contribute to future generations of stars. But during this long, slow decay, the remnants are still dynamic. They continue to accelerate cosmic rays, sculpt interstellar clouds, and glow in various wavelengths of light, each telling a piece of the story of the star that died and the elements it scattered. Studying these fading echoes helps us understand the complex processes of galactic evolution and the intricate ways matter is recycled and redistributed throughout the universe. The ongoing quest to understand supernovae is a testament to humanity's insatiable curiosity. It's a journey that combines the awe of looking at distant cosmic fireworks with the rigorous precision of scientific inquiry. Each new observation, each refined theory, brings us closer to understanding not just how stars die, but how galaxies evolve, how the elements essential for life are created, and ultimately, how our own existence is fundamentally linked to these spectacular, life-giving explosions. We are, in every sense, connected to the stars, and their fiery deaths are an indelible part of our cosmic heritage. Our journey of discovery through the universe is a continuous one, forever guided by the magnificent, powerful flashes of stellar death. Imagine now stretching your mind not just across space, but across time itself. When we observe a supernova in a galaxy that's, say, 1 billion light-years away, the light we are seeing left that star 1 billion years ago. That means we're not just seeing an explosion, we're seeing what the universe was like 1 billion years ago. It's like a natural time machine. By studying supernovae at different distances, we build a cosmic photo album of the universe at various stages of its development. We can see how galaxies were different, how stars were forming more actively, and how the very chemistry of the cosmos was less evolved. This time-traveling capability is crucial for understanding the universe's grand story. The light from incredibly distant supernovae is also stretched, or redshifted, by the expansion of space itself. Imagine a wave drawn on a rubber band. As the rubber band stretches, the wave gets longer. Similarly, as light travels across the expanding universe, its wavelengths get stretched, shifting towards the red end of the spectrum. By precisely measuring this redshift, astronomers can figure out just how much the universe has expanded since that supernova's light began its journey. This is another layer of information that helps us chart the universe's history and confirm its accelerating expansion, revealing the pervasive influence of dark energy. Supernovae also serve as incredible, naturally occurring laboratories for testing the most extreme physics. Imagine trying to recreate the conditions inside an exploding star here on Earth. It's simply impossible. The temperatures, pressures, and densities are far beyond anything we can achieve in our laboratories. But by studying the light, the neutrinos, and the potential gravitational waves from supernovae, we gain direct insight into how matter behaves under these incredible forces. This helps us refine our understanding of fundamental particles, the structure of atomic nuclei, and even the very nature of space and time. They offer unique glimpses into the extreme limits of physical laws, pushing the boundaries of human knowledge in ways no terrestrial experiment ever could. Even after their dazzling initial flash, the fading supernova remnants continue to be a rich source of information for thousands and millions of years. Imagine tracking one of these immense, expanding bubbles of gas and dust. Over time, the material cools, condenses, and eventually merges back into the vast interstellar medium, ready to contribute to future generations of stars. But during this long, slow decay, the remnants are still dynamic. They continue to accelerate cosmic rays, sculpt interstellar clouds, and glow in various wavelengths of light, each telling a piece of the story of the star that died and the elements it scattered. Studying these fading echoes helps us understand the complex processes of galactic evolution and the intricate ways matter is recycled and redistributed throughout the universe. The ongoing quest to understand supernovae is a testament to humanity's insatiable curiosity. It's a journey that combines the awe of looking at distant cosmic fireworks with the rigorous precision of scientific inquiry. Each new observation, each refined theory, brings us closer to understanding not just how stars die, but how galaxies evolve, how the elements essential for life are created, and ultimately, how our own existence is fundamentally linked to these spectacular, life-giving explosions. We are, in every sense, connected to the stars, and their fiery deaths are an indelible part of our cosmic heritage. Imagine now that we could zoom out even further, beyond the scale of single galaxies, to witness the universe on its grandest scale, the cosmic web. This is the universe's scaffolding, where galaxies and galaxy clusters are strung along vast filaments, separated by immense, nearly empty voids. Supernovae, through their incredible energy and the matter they disperse, play a subtle yet profound role in shaping this colossal structure. The powerful outflows and winds driven by intense supernova activity in active star-forming galaxies can push gas out of the galaxies themselves, affecting the distribution of matter not just within a galaxy, but also in the intergalactic medium that lies along these cosmic filaments. It's like a colossal, invisible breath, influencing the very architecture of the cosmos. The energy injected by supernovae also contributes to heating the diffuse gas that exists between galaxies in these cosmic filaments. This heating can prevent some of that gas from cooling and collapsing to form new stars and galaxies, thereby regulating the overall growth of cosmic structures. So, while a single supernova is a flash in the pan on cosmic scales, their collective action over billions of years has a direct hand in determining where the universe's matter clumps together and where it remains stretched out and sparse. They are the constant, energetic stirrers of the cosmic soup. The sheer longevity of a supernova remnant's influence is something to truly ponder. While the visible light fades within months, the mechanical energy and the enriched material from the explosion continue to ripple through the interstellar medium for millions of years. Think about it. A single event from eons ago is still influencing the density, temperature, and chemical composition of gas clouds today, far from its original source. These long-lived echoes are a testament to the fact that nothing truly vanishes in the universe. It merely transforms. The atoms scattered by a dying star will eventually find a home in a new star, a new planet, or even a new form of cosmic dust, perpetuating the cycle. Looking far into the future, as the universe continues to age and star formation slows down, the rate of supernovae will also decline. In the distant cosmic future, when most of the available gas has been locked away in stars or blown out into intergalactic space, these spectacular explosions will become increasingly rare events. The cosmic fireworks will become fewer and further between, marking a quieter, though perhaps still active, era of the universe's existence. But even then, the compact remnants of past supernovae, the neutron stars and black holes, will continue their silent, profound existence, dancing through the twilight of the cosmos. Supernovae are more than just astronomical phenomena. They are foundational to the very existence of complexity and life in the universe. They are the cosmic bridge between the simple elements of the Big Bang and the intricate, diverse world we inhabit. They remind us that destruction is often a necessary precursor to creation, and that the universe is a relentlessly dynamic and interconnected place, constantly undergoing transformation, fueled by the spectacular lives and deaths of its stars. Supernovae are more than just astronomical phenomena. They are foundational to the very existence of complexity and life in the universe. They are the cosmic bridge between the simple elements of the Big Bang and the intricate, diverse world we inhabit. They remind us that destruction is often a necessary precursor to creation, and that the universe is a relentlessly dynamic and interconnected place, constantly undergoing transformation, fueled by the spectacular lives and deaths of its stars. Imagine looking at the cosmos and recognizing that even the seemingly empty space between stars is alive with activity, often driven by the echoes of past supernovae. We've discussed the brilliant flash, the expanding remnant, and the dense objects left behind. But the influence of these explosions extends far beyond what our eyes can see, or even what our telescopes can easily detect. The immense energy released heats the interstellar and intergalactic gas, influencing the way it moves and behaves. It's like a cosmic heater, subtly warming vast stretches of the universe, impacting the conditions for future star formation. These explosions also amplify the weak magnetic fields that permeate galaxies. As the supernova shockwave rips through space, it can compress and twist existing magnetic field lines, making them much stronger. These amplified magnetic fields then play a crucial role in shaping nebulae, guiding the flow of gas, and even influencing the propagation of cosmic rays. So, the death of a star creates not just a spectacular visual, but also a complex, invisible web of magnetic forces that continue to sculpt the galaxy long after the light has faded. The sheer number of supernovae happening across the universe at any given moment is truly mind-boggling. While our own Milky Way might only see 1 or 2 per century, multiply that by the billions of galaxies in the observable universe, and you realize that countless stars are ending their lives in spectacular fashion at every instant. This constant barrage of explosions ensures that the cosmic recycling plant is always operational, continually breaking down old stellar matter, forging new, heavier elements, and distributing them far and wide. It's a relentless, universal process, ensuring that the ingredients for new stars, planets, and perhaps even new forms of life are always being replenished across the vast cosmic canvas. Every single one of these distant flashes offers a unique data point, a fleeting opportunity to learn more about the universe's history and its fundamental laws. They are the universe's own experiment, playing out across cosmic scales, providing us with invaluable insights into the extremes of stellar physics, the composition of the early universe, and the forces that drive cosmic evolution. It's a profound thought that the most destructive events in the cosmos are also among the most vital for creation and understanding. The knowledge we gain from them not only satisfies our curiosity but deepens our appreciation for the intricate, violent, and beautiful processes that have shaped everything around us, and indeed, ourselves. The story of supernovae is truly the story of the cosmos itself, forever unfolding in a dance of light and shadow, creation and destruction. And so, we complete our journey through the awe-inspiring world of supernovae. We've seen how these magnificent stellar explosions are far more than just brilliant flashes in the night sky. They are the universe's ultimate alchemists, tirelessly forging the very elements that make up every atom around us, from the iron in our blood to the silicon in the rocks beneath our feet, and the precious gold we cherish. Without their cataclysmic power, the cosmos would remain a much simpler, barren place, devoid of rocky planets and the intricate chemistry necessary for life. We've explored how these powerful blasts act as the grand architects of galaxies, their expanding shockwaves sculpting nebulae, triggering the birth of new stars, and even blowing immense bubbles through the interstellar medium. We've seen them as cosmic lighthouses, their consistent brilliance allowing us to map the universe's vast expansion and discover the mysterious force of dark energy. And we've marveled at the extreme remnants they leave behind, the impossibly dense neutron stars and the enigmatic black holes, objects that push the very boundaries of our understanding of physics. From the first, primordial supernovae that seeded the early universe with the initial heavy elements, to the ongoing explosions that continue to enrich galaxies today, these events are central to the universe's continuous cycle of creation and renewal. They remind us that destruction in the cosmos is rarely an end, but almost always a spectacular, necessary prelude to new beginnings. The very atoms that compose your body have traveled an unimaginable journey through stellar furnaces and supernova explosions, linking you directly to the fiery heart of the cosmos. So, The next time you gaze up at the night sky, whether you see a familiar constellation or perhaps, one day, witness the incredible brightening of a distant star, remember the extraordinary story of the supernova. Remember the immense power, the profound artistry, and the deep, enduring connection these stellar deaths have to every part of the universe and to every breath you take. They are the universe's most dramatic act of self-renewal, ensuring that the grand cosmic ballet of light, matter, and life continues on, endlessly unfolding across time and space.